we study these two sections together as one. In this video, we'll discover the inverse trigonometric functions, learn about domain and range of these functions, and see how to evaluate these functions using pencil and paper and also on the calculator. Precalculus Online starts now. In these combined sections, 7.1 and 7.2, we'll look at inverse trig functions. And so let's start with the quick review. Number one, in order for the inverse of a function to exist, the function must be 1-to-1. Number two, to determine if a function has this property, being 1-to-1, the graph of the function must pass the horizontal line test. Number three, determine which of these functions has this property and which do not. So which of these are 1-to-1? Well, the first one is the exponential function, which is 1-to-1. The second one is the parabola. And there are plenty of horizontal lines that pass through two different points on the parabola, so this one's a no. And the last one is the sine function. And so if you'll look at exploration number 1 in GeoGebra, where you can find the link on the courses page, then this exercise goes through and talks about how this is not a 1-to-1 function because it's sinusoidal, it's always repeating. For example, right here, there's several points right here where it goes through the sine curve. But we do want to be able to find the inverse sine function to help us do some things in trigonometry. And so you'll remember from when we talked about the parabola and it being not a 1-to-1 function, what did we do? Well, we just came back and we just sort of removed half of it. And we ended up with a restriction on the domain. That then created a 1-to-1 function. So you're going to do the same thing with the sine function. So in this exploration, what I want you to do is to come up with an interval for the domain where sine is, in fact, 1-to-1. Once you do that at this time, stop the video, and then I'll tell you what some of the answers were, or could have been, when you resume the video. So go ahead and do that now. All right, so hopefully you had a chance to do that. There are several answers that you could have chosen for how to restrict the domain of the sine function so that you produce a 1-to-1 function. One of the common answers that we see is to start right here at pi over 2 and take all of this going down unto 3 pi over 2. This does, in fact, create a 1-to-1 function, and we could restrict the sine function to be defined only on this domain so that we could find a valid inverse for that function. And everything would be fine. That's just not the one that people chose over time. Instead, they went for the one that was closer to the origin. And they went from negative pi over 2 all the way up to pi over 2. So this one is 1-to-1. And it has the additional benefit that it's defined at 0. And they put value into that. The other answer would have worked, it's just historically not the one that we use. So example 1, let f of x equal sine of x, then f inverse of x is equal to the inverse sine of x on the restricted range listed above, which is from negative pi over 2 to pi over 2 from the graph on the previous page. And then it says find f inverse of root 2 over 2. So what this is asking for is the inverse sine of root 2 over 2? Well, if we look at the unit circle, we want the inverse sine to be defined on this interval from negative pi over 2 to pi over 2. That means the answers that I can produce for the inverse sine have to come from this right-hand portion of the circle. Further, they have to be numbers between negative pi over 2 and pi over 2. So even though, suppose that we wanted to end up with the angle that produced this point, we're not allowed to use this positive angle that would be, say, 5 pi over 3. That is not allowed. You would instead have to use the back angle, the negative angle, negative pi over 3, for example. So you have to maintain this interval whenever you're producing answers for the inverse sine. So let's take a look. For this particular answer, we're looking at where the sine is equal to root 2 over 2. Well, we know the rest of that point on the unit circle has an x value of root 2 over 2, and that this angle is pi over 4. So the inverse sine of root 2 over 2 is pi over 4. Always remember that when you're doing the inverse trig function of something, you are looking for the angle that produced the result. So inverse trig functions produce angles. That's what you want to get as an answer. I should also mention one other thing. You'll sometimes hear me say arc sine. This is sort of an old-fashioned terminology, but it was one that I grew up with, so I sometimes say that as well. And that's the same thing as inverse sine. And that also comes from an old terminology where what they were looking for when they were finding the inverse, quote unquote, was actually the arc of the circle, which we know corresponds to the angle. So that's where that comes from. So I'll say that every once in a while. And of course there are others, arc cosine, arc tangent, things like this. And also, another valid way of writing this is just arc sine. Like that. So you may see that in some literature somewhere or in a different textbook. Let's look at example number 2. Find the sine of the arc sine of 0.2. So in this case, here is the inverse sine of 0.2. I'm just going to represent that by a theta. That means we're going to produce the theta there. And then, secondly, we're going to have the sine of that angle. Well, let's take a look at the unit circle. And since we're doing inverse sine, I only really need the right half. The 0.2 ends up being the y-coordinate. So there's a point on the unit circle that is x, some x, don't know what it is. And then the y is 0.2. And the reason the 0.2 is the y is because we're doing the arc sine. So that arc sine means that there was an angle theta that we took the sine of in order to get 0.2. Well, this is one of those that's sort of predestined to work. If you're going to take the sine of the arc sine of 0.2, then the answer is going to be 0.2. And that is because, in some sense, the sine and the arc sine will cancel as long as you can take the arc sine of 0.2. The 0.2 has to be in the domain of the inverse sine function. Well, it is, because there is an angle that we can take the sine of to get 0.2. And then when we actually take the sine of that angle, we get 0.2. That one works out well. Let's see an example where it doesn't quite work out as well as you'd like. Example 3. Find the arc sine of the sine of 5 pi over 3. Well, in this case, let's look at the circle here. Here we have a theta, 5 pi over 3, which is this angle here. Now, what we would want to do is say, well, I'm taking the arc sine of the sine, those cancel, and that just leaves me with 5 pi over 3. And that is not correct. And the reason is because 5 pi over 3 is not in the range of the arcsine. Remember that the arcsine has to have a range that goes from negative pi over 2 to pi over 2. So all of the answers from doing the inverse sine function have to live within this range. 5 pi over 3 does not. So let's take another stab at it. And we'll go with, here is the point at 5 pi over 3. And that point would be 1/2, comma, negative root 3 over 2. And then the question is, what angle would produce this point on the unit circle, but only if I represented it from negative pi over 2 through pi over 2? And the answer is this angle would be negative pi over 3. And that's the answer. So you have to sort of finesse the angles to get them within the right range, even though they do represent the same point on the unit circle. Let's look at the exploration number 2. I want you to do the same thing that you did before with sine, but this time do it with cosine. You want to find an interval for the domain where the function becomes 1-to-1, and then we can take the inverse. Go ahead and pause the video at this time and complete the exercise. All right. So you should have been able to come up with a domain here. The correct domain that we use is from 0 all the way to pi. And that is a restriction of the domain for cosine, and so that means that the arc cosine function has a range of 0 to pi. In other words, all answers that we get from taking the inverse cosine are going to be on the upper half. And hopefully you can see what we're doing. Since cosine represents the x values, here we're getting every x value possible represented one time uniquely by using the upper half circle. So it goes from 0 to pi. Were there other intervals that would have worked? Yes, but historically they have not been chosen to work. So we use 0 to pi. Example 4. Find the arc cosine of root 3 over 2. Well, let's take a look at the unit circle. We're looking for the angle whose cosine is root 3 over 2. We know that cosine is the x value. So there is this point on the unit circle where the x value is root 3 over 2. The y value is 1/2, although that's not as important at this point. But also, this is the point that is in the restricted interval from 0 to pi. And so this is the one that we choose. Let me show you the one that we did not choose. We did not choose this one down here, even though it still has the same x value. It has the different y coordinate, and it's not the one that we use. And then the question is, what is this angle? That angle is pi over 6. Example 5, what is the arc cosine of the cosine of 5 pi over 3? Again, this is the example where you would want to just cancel off the cosine and the arc cosine and say that the answer is 5 pi over 3. But that's not right, because 5 pi over 3 is not in the interval from 0 to pi. So instead, we draw the picture, and we draw the angle 5 pi over 3. And this has an x-coordinate of 1/2. We'll call that y1. 1/2 y1. And this angle is in quadrant 4. We're not allowed to use quadrant 4. We can only use quadrants 1 and 2. So what we're going to do is we're going to create the vertical line that passes through that point. And we choose the vertical line because I need the x value to stay the same. That produces this point, which is 1/2, comma, let's say y sub 2, a different y. And this new point is in the correct quadrant for doing arc cosine. So the question is, what is that angle? And that angle is pi over 3. So the arc cosine of the cosine of 5 pi over 3 is pi over 3. Example 6. What is the cosine of the arc cosine of root 2? Again, this is one of those where you just want to cancel and say that the answer is root 2. That is not correct. And the reason for that is because the value of root 2 is approximately 1.4, which is greater than 1. And we know that the cosine function has a maximum value of 1. So therefore, there is no angle that you can take the cosine of to get root 2. So the cosine of theta equals to root 2 has no solution. And therefore, this arc cosine of root 2 is undefined. And that's the answer for this one. Example 7. What is the arc cosine of the cosine of negative 3 pi over 4? Let's draw the unit circle. Draw the angle. Negative 3 pi over 4 is right here. This point is in quadrant 3. We're not allowed to use quadrant 3 for cosine. So we're going to go ahead and go up using a vertical line to this point. Not quite drawn to scale. It's okay. And then the angle that we can use is this angle that's in quadrant 2. And what angle would have the same x coordinate for the points as the negative 3 pi over 2, 3 pi over 4 rather? That is positive 3 pi over 4. So the strategy again is to project up into one of the quadrants where you can find a valid answer based on the range. For cosine, that's quadrants 1 and 2. For sine, that is quadrants 1 and 4, but using the negative versions of the angles in quadrant 4. Next, let's talk about the arctangent function. The arctangent function has a similar restriction to the sine function. It is restricted to having values that are from negative pi over 2 to pi over 2. But notice that this interval is an open interval. It does not include the endpoints. But otherwise, it's the same as sine. Another thing to note is, what can you take the arctangent of? You can take the arctangent of any real number. So this is defined for all real numbers. Example 8, find the inverse tangent of root 3. So one of the things that I would do in the first quadrant for your unit circle is I would add in the tangents. Now, you won't have access to that on the test, but you can quickly reproduce these. You know that the 45-degree angle produces a 1. Because that's where the coordinates are the same, and tangent is the ratio of the y over the x. Well, if the y and the x are the same, then their ratio is 1. But this lower number here is going to be the smaller of the other numbers that we know, root 3 over 3, and the higher number here is just going to be the root 3. course, you can remember that this is 0 and that at the pi over 2 it's undefined because it basically amounts to a vertical line. And with that, example 8 is very simple. What is the arctangent of root 3? It's this angle, which is pi over 3. Example 9. Find the inverse function of y equals 5 cosine of x plus 3 and find the domain of the inverse. So if we want the inverse, we proceed as normal. So y changes to an x, and x changes to a y, and we get x is equal to 5 cosine of y plus 3. Now we want to solve for y. So next I'm going to move the 3 over. We get x minus 3 is equal to 5 cosine y. Divide both sides by 5. We get x minus 3 over 5 is equal to cosine of y. And then the question is, how do I now get into the cosine function? Well, the trick is to take the arc cosine of both sides. And the arc cosine of the cosine of y is going to be the y itself. And we set this up so that it will work. So y is equal to the arc cosine of x minus 3 over 5. Let's rewrite that as the inverse function, if you want. So f inverse is equal to the arc cosine of x minus 3 over 5. And then the question is, what is the domain of this inverse function? Well, the domain has to be the set of x's that you can actually take the arc cosine of. You can take the arc cosine of any number from -1 up to 1, because that is the range of the cosine function itself. So what values of x give me a result that's between -1 and 1 whenever you take x minus 5 over 3. And you just solve this, what I call a triple inequality. It's a triple-sided inequality, I guess. So it's a -5 is less than or equal to x minus 3. So x is less than or equal to 5. We get that by multiplying all three parts by 5. And then I'm going to add 3 to everything. So we're going to get -2 is less than or equal to x is less than or equal to 8. So the domain is from -2 to 8. And that should not be a surprise, because if you look at the original function, the domain of the inverse is the same as the range of the original. Well, the original had a median of 3 and an amplitude of 5. That means it started at 3 and went up 5 to 8 and then down 5 to -2. So there's where the -2 and the 8 come from. It's the max and the min of the original cosine graph of the original function that we started with. Let's look at more inverses. In example 10, we want the tangent of the arc sine of root 2 over 2. So let's draw the unit circle. Let's make sure we understand that when we are doing the arc sine of root 2 over 2, we are producing an angle theta. Go ahead and draw that theta on the unit circle. Since sine is the y-coordinate on the unit circle, this is some x and root 2 over 2. And this angle is the theta. And the question is, what theta produces this point on the unit circle? Well, that's a common point on the unit circle, and that would be the tangent of pi over 4. And now we can work out tangent of pi over 4. We know that the other part of this coordinate point is a root 2 over 2 as well. And so tangent is the y-coordinate divided by the x-coordinate. Root 2 over 2 divided by root 2 over 2, which is 1. Let's look at example 11. What is the cosine of the arcsine of 1/5? So again, let's acknowledge that we are finding a theta. This theta is going to be in quadrant 1 because we are taking the inverse sine of a positive, and the inverse trig function of any positive number is always going to be in quadrant 1. It's the negatives that could be in quadrant 2 or 4. So let's go ahead and find this point. I'll draw it right here, and we recognize that what we have is x comma 1/5. Again, that is because the sine finds the y-coordinate on the unit circle. This is theta. Now, in order to find the cosine of this angle, we are going to need to figure out what the x-coordinate is. So I'm going to go over here and let's do the Pythagorean theorem. Bring this down. I'm going to set this up as x. I can set this up as 1/5, and the hypotenuse to be a 1. Let me show you how that works. So we get x squared plus 1/5 squared is equal to 1 squared. So x squared plus 1 over 25 is equal to 1. X squared is equal to 1 minus 1 over 25. X squared is equal to 24 over 25. And x is equal to 2 root 6 over 5. It's positive because we're in the first quadrant. And now, since I set this up as a unit circle, the cosine of the angle theta is just the x-coordinate, so it's 2 root 6 over 25. That is one choice. Another choice, and you'll see this probably more frequently, is to set up the circle, draw, and this is just any circle, draw the triangle in the correct quadrant, and then acknowledge that the sine of theta is equal to y over r. But in this case, we're saying it's equal to 1 over 5. So we can go ahead and assign 1 to the y-coordinate and 5 to the hypotenuse, or the radius. And then that leaves us just to find the x. So this works out very much in the same way. X squared plus 1 squared is equal to 5 squared. Simplify that to x squared equals 24, and x is equal to 2 root 6. Positive again because we're in the first quadrant. But then you're basically taking the cosine of this theta, and the cosine of that theta is the x over the r, which is 2 root 6 over 5. So you get the same answer either way. This side, the first way that we did it was based on the unit circle. The second way we did it was based on some arbitrary circle that we created. It's fine. It works out both the same way, but probably this second way is the one you'll see most often worked out in by instructors and in worksheets and things like that. Let's take a look at the other trig inverses. They do exist. And so what is the domain for the arcsecant function? It's negative infinity to negative 1, closed, union 1 to infinity, closed at 1. So it's everything except the interior negative 1 to 1 interval. The range is a little bit different here. It's going to be 0 to pi over 2, open at pi over 2, union pi over 2 to pi. So it's everything from 0 to pi except for pi over 2. And that's because that is where the cosine is equal to 0. And the secant function is the reciprocal of cosine. So you would end up with a 0 in the denominator, which you can't have. Now the alternative version here that you need to know for using a calculator is that y is equal to the arc cosine of 1 over x. So before, when you wanted to find the secant of something, you took the cosine of it and then you took the reciprocal. Remember, for inverses, you do the opposite of those things and in the opposite order. So in order to find the arcsecant, you need to take the reciprocal of the x first and then take the arc cosine. Next is cosecant inverse. This has the same domain as the secant function, but it has a range that is more similar to the sine function for obvious reasons. It's more closely related to sine, and the alternative version is the arc sine of 1 over x. Cotangent has the entire real line as the domain. It has a range that goes from 0 to pi, but it's open on both ends. So this one is different from tangent. Tangent went from negative pi over 2 to pi over 2. This one goes from 0 to pi. So it's more closely related to cosine in that respect. The alternative version is to take the arctangent of 1 over x. Let's look at the arc cotangent of root 3 over 2. So in this case, let's look at the circle. So we are looking for the point on the unit circle that we can express as x over y. But how do we get that? So root 3 over 3 is equal to 1 over root 3. That's the unrationalized version. And then how did we get this? Well, let me just divide each of the numerator and denominator by 2. And then I'm going to say that that's x and that's y. So, where is the x 1/2 and the y root 3 over 2? That is pi over 3. So the answer is pi over 3. If you'll go ahead and take out your TI-84, let's work through some of these examples so that you can see how to do these. Number one, make sure you're in radians for this. And then find the value of the arc sine of 0.75. So if you just type that in, be sure and use shift and then sine to get the arc sine, not the 1 over x button. Those are different. And you should get 0.848. Next, what is the inverse cosine of negative 0.3? That's going to be in quadrant 2 because it's arc cosine. And you should get 1.875. Next, we want the inverse cosecant of 3.51. Well, we don't have an inverse cosecant function on a calculator, so I need to rewrite this in the alternative form. The alternative form involves using arcsine and the reciprocal of the number I want to take the inverse cosecant of. So it's the inverse sine of 1 over 3.51. If you type that in, you get 0.289. Finally, example 13. Simplify the cosine of the arctangent of u in terms of u. So this turns out to be a very valuable skill when you get to Cal 2, is how can you express some quantity that has some trig and inverse trig stuff going on around it. The trick is to do the following. Let's draw this in the first quadrant. Let's go ahead and declare that the inverse tangent of u is going to be theta. So we have theta here. But that means that the tangent of theta is equal to u, and in particular, if it's just a u, I can represent that as u over 1. Now, what was tangent? Tangent on the unit circle is y over x. So I'm going to go ahead and make u be the y distance and x be a 1. And then in order to finish this, I need to find the hypotenuse h. Let me use the Pythagorean theorem. So we're going to have 1 squared plus u squared is equal to h squared. And so h is equal to the square root of u squared plus 1. You have to be careful with the plus or minus. You'd have to have some more information about this to determine if it should be a minus square root. So we're just going to go with the regular square root in this problem. And so h is the square root of u squared plus 1. And now what we're down to is finding the cosine of the theta angle, where theta is represented by this picture above. Well, cosine is x over r, and so that's going to be 1 divided by the square root of u squared plus 1. And usually for these problems in calculus, we do not rationalize the denominator. So let's go ahead and leave it as that.